We just discussed geometric distortions and how they produce undesirable effects in images. We're talking about radial distortions as well as tangential distortions. In a perspective image, you generally want to remove these effects. But it turns out that there is a scenario, one particular application, where we want to actually introduce geometric distortions into the system, and that's wide-angle imaging. So think about the following scenario. Let's say that you wanted to capture a hemispherical field of view, like this. And let's say the imaging system is looking up. You have the pinhole right here, effective center of projection, and you have an image plane underneath that. If you wanted to capture this complete hemisphere, you would have to have an image plane that is infinite in extent in both dimensions. That's just not practical. Secondly, even if you were able to do that, let's say you have an object sitting in front here. This object would be reproduced well in this image, but as the object moved to the periphery of your hemispherical field of view, it's going to be stretched severely in the image. So you have nonlinear resolution effects as well. For all these reasons, what you want to do is to design a wide-angle imaging system by introducing geometric distortion into it so that it can take the complete field of view and compress it down to a small area where you would place your image sensor. So there are two ways to do this. One is to use lenses, and the second is to use mirrors. Let's talk about lenses first. So here is an example of a fisheye lens. This was first introduced by Miyamoto back in 1964. The fisheye lens has been designed to have a very large field of view, 170 degrees in this particular case, and uses a series of what are called meniscus lenses. A meniscus lens is convex on one side and concave on the other side. This allows the system to bend light severely, especially those rays of light that are more away from the optical axis, towards the periphery of the field of view. So this is a meniscus lens right here, this is another one, and then a series of other lenses which finally compress the field of view onto this small image sensor. Now actually bending light to arrive in a small area, compression, is not that hard. What's really hard is making sure that the image is well focused everywhere, the entire field of view. So these are fairly sophisticated optical designs. Here's an example of a fisheye lens right here. And one thing that I do want to mention is the viewpoint of the fisheye lens. So you have these rays of light coming in, and they don't necessarily intersect at a single point, as in the case of your pinhole camera, but as long as it is a small set of points, a small locus of points, it's fine. You can assume it to be a single viewpoint system. I mention this because it's important for any imaging system. It's very convenient, especially in computer vision, for it to be a single viewpoint system. Because if I see some part of the field of view from this viewpoint, and I see another part of the field of view from this viewpoint, it's very difficult to recreate an image that is perspective of this entire field of view without knowing the three-dimensional structure of the entire scene. So you really want single viewpoint systems in computer vision. Okay, so here is an example of a fisheye lens again. And this fisheye lens has a 180-degree field of view. This is the image captured by the lens. It's essentially sitting close to ground level looking up. And since you've satisfied the single viewpoint constraint, it more or less has looking at the world from one point in space. Therefore, you can take any part of this image. Although it is distorted, you can take any part of this image and use software to map it into a pure perspective image. And that's really important. So you can literally build a little viewer, write a small piece of code that allows you to look around the scene from that same viewpoint. You're essentially creating a software camera that uses nothing but the single image to look around in different directions. Now, one of the challenges with the fisheye lens is that you can't go well beyond a hemisphere. It's very hard to design a lens-based system that can give you much more than a hemisphere. So here is a very interesting design by Ricoh. It's called Ricoh's Theta camera, and it uses two fisheye lenses. And so this fisheye lens ends up seeing this part of the world, and this fisheye lens looks at the back part here, the back hemisphere, and the two hemispheres actually overlap a tiny bit. And what's nice here is that the design is such that the two have been placed very close together. That is, all the imaging hardware has been packed in between these two lenses so that the viewpoints of both these systems are close enough that you can assume them to be at the same point. This allows you to stitch these two hemispheres together to create a complete spherical image. And that spherical image then allows you to look in various directions. There are versions of this camera both that produce still images as well as videos. Okay, so I mentioned that it's hard to design a lens-based system that can go well beyond a hemisphere. There are applications where you do indeed want not the hemisphere, but a panorama, say for instance, which goes all the way around 360 degrees. One application would be video conferencing. So you have an equator here, you would like an imaging system that captures a complete 360-degree view and which has a field of view which may be, say, plus or minus 45 degrees with respect to the equator. This is very hard to do using a lens system. And the way you do it is by introducing mirrors into the imaging system. So let's now talk about what you can do with mirrors. We'll start with planar mirrors. Here you have a camera, and this is your pinhole or center of projection of the camera. This is your image sensor, and this is your field of view. So now think about what happens if you place a mirror in the field of view of this camera as such. Well, what happens is that this real camera essentially gets reflected by the mirror to create a virtual camera. So in other words, the viewpoint is reflected to this point right here, equidistant from the mirror, and the field of view is also reflected or rotated right here. So you have a virtual camera in place of your real camera. And so now what if you place another mirror in the field of view of this virtual camera? That's mirror 2. Then this virtual camera is going to be reflected again to create another virtual camera. So all this to say that you can use planar mirrors to play lots of games and manipulate or move around the position and the field of view of a real camera. This is used in many different applications. It's called optical folding. And actually, this technique for imaging is called catadioptrics. Catoptrics is the use of mirrors, and dioptrics is the use of lenses. This kind of a system uses both lenses and mirrors, and therefore is a catadioptric system. Now, in doing this, in playing this game, we have changed around the position and the orientation of the field of view, but we haven't changed the size of the field of view. We have done nothing to the size of the original camera's field of view. The virtual camera's field of view is exactly the same in terms of the size of the field of view. What we are interested in, as you know, is wide-angle imaging. So the question is, how do we enlarge the field of view of this real camera right here? We do this by using curved mirrors. So here is an example, a design that uses a hyperbolic camera. So here's your hyperbola right here. We know that a hyperbola has two foci. This is focus 1 and this is focus 2. And what happens here, the interesting thing that happens, is that all the rays of light that come in the direction of this first focus, focus 1, all the rays coming in from the scene towards focus 1 get reflected by this hyperbolic mirror towards focus 2. And so that is where you would place the center of projection or pinhole of your lens camera, right here. And that would ensure that you would capture an image which is the reflection from this hyperbolic camera, but it is a reflection of the scene as seen from a single point, which is from focus 1. So the thing to note here is that you can go well beyond a hemisphere in this case. So consider this ray of light. This one right here, it corresponds to a seen ray that comes in from beneath the equator, beneath the line that passes through focus 1 right here. So you can manipulate, you can choose the parameters of your hyperbola so as to control the field of view of your wide-angle system based on the application at hand. So here is such a system that uses a hyperbolic camera right here. This is where you would attach your lens camera. And if I hold it up here, it actually captures an image which goes down in its field of view, but also well above this plane. You can go up, say, 45 degrees or so, which is hard to do using a lens camera. So if you had a video conferencing application, you would place this in the center of the table, and it would be able to get a field of view which is, say, plus minus 45 degrees going full 360 degrees. Now here is another way you could do this, another design which uses a parabolic mirror. The parabola has a single focus which sits within it. You can say it has a second focus too, which is at infinity, but what it does is it takes all the rays of light that come in the direction of its focus right here and reflect these rays to be parallel to one another, straight up, all the rays. If I had a ray coming in from here, it would also go parallel to the optical axis. So in this case, you don't use a perspective lens or camera, you use what's called an orthographic lens or a telecentric lens to capture these parallel rays of light and then create an image up here. So let's take a look at an image taken with a mirror camera. Here is the image. And I should note that this black disc that you see in the center, this actually represents one of the downsides of using mirror-based wide-angle cameras. So this is where the mirror sees the lens itself. So this is sort of the blind spot of your imaging system. On the positive side, you have a field of view here which goes well beyond 180 degrees. And since we have satisfied the single viewpoint constraint, which means that the viewpoint of this imaging system lies at the focus of the parabola, you can take, of course, any part of this image that I'm showing you here and convert it into a perspective image. You can use a viewer to pan around, or you can map this peripheral part of this image, this annulus right here, and map it into a cylindrical panorama that looks something like this. This is just a visualization to show you all the things that you can do in software with this single image. And of course, in most applications, you would have video and do this at, say, 30 frames per second. So for certain domains, wide-angle imaging, panoramic imaging is very, very useful and has become very popular. In fact, today you can find various devices that have attachments that convert the camera of the device into a panoramic camera that uses mirrors. So here is Sony's Bloggie on the left here. And so you see that it has a little attachment here which you can flip over. If you want to keep it on a table, it would go like this, capture a panorama, or you can hold it up like this to do the same. On the right, you see an attachment for iPhones, which would take the iPhone camera and convert it into a panoramic camera. Okay, so now I want to mention that this use of curved mirrors is new in the case of wide-angle imaging, but it's been around for another reason for many, many decades, for a long time, centuries for that matter, and that is the design of telescopes. So in the case of a telescope, what you're trying to do is look at an object that is really far away. So you're really talking about a very narrow field of view, but since the object is really far away, it's really dim, and you would like to be able to collect as much light as possible from the object. For this, you use a wide aperture. And so that's where curved mirrors come in. In this case, you're not using a convex parabola, but rather a concave parabola. So here is an example. This is a concave parabola. In the case of the James Webb Space Telescope, it happens to be 21 feet in diameter. And so there is no known method for manufacturing a single mirror that's 21 feet, curved mirror that's 21 feet in diameter. So the way this is done in practice is to create these small little segments. That's what you're seeing here, these little hexagonal segments. Each one is a shallow mirror, curved mirror. And these are then put together, tiled together to create the complete mirror. And this mirror focuses the light coming in almost parallel onto its focus, which is where you would place the image sensor. That's the complete imaging system. This turns out to be golden in color because it's gold plated, because in this particular application, one is more interested in certain wavelengths of light that are best reflected by gold plating. Now, do you like scallops? Oh, let me give you a little recipe for scallops. So you take your scallops and you sprinkle a little bit of salt, a little bit of pepper, mix it up, keep it off to the side. And now you take a pan or a skillet, heat it up, throw a chunk of butter on it, and then you're going to put your scallops on your heated pan and sear it. You're going to brown it on both sides, cook it. And then you take your scallops and keep it off to the side. Now in the same pan, you're going to throw in some more butter. Butter is always good. Throw in some more butter, a little bit of garlic, and you put in about half a cup of white wine, a little bit of chicken broth, and you let it simmer. You let it simmer, you reduce it. You make a roux out of it, a sauce. And so when it's reduced, then you're going to squeeze in some lemon juice, and that becomes your sauce. You pour your sauce over the scallops, and you garnish it with some parsley, and you get this. Now I know what you're thinking. How did this turn into a cooking class? Well, blame it on the scallops. We want to talk about scallops. So let's take a look at one scallop here. This is a scallop in its full glory. So you have the flesh of the scallop right here. This is the part that you end up eating. And then you have the shell here. But what I want to draw your attention to are these tiny little blue dots that you see here. These tiny little blue dots. It turns out that each one of them is an eye. Each one of these has a concave parabolic mirror inside of it that takes light from a narrow field of view and then focuses it, very much like a telescope, onto a single receptor, a pixel. So with hundreds of these eyes around its periphery, the scallop is able to get a distribution, a pretty good idea of what the distribution of light is all around it. Just absolutely amazing. Just think about it. Nature creating an eye with concave parabolic mirrors. Now I want to show you the last example of wide-angle imaging. I would say that this one is half biological and half computational. So here is a high-resolution image of a person, and if the image is of really high resolution, what you should be able to do after the fact is zoom into one of the eyes of this person and see something like this. So the point that I'm trying to make here is the cornea of your eye, which is what you're seeing here, has a thin film of tear on it, which makes it behave like a reflective surface, a mirror, a curved mirror. Not a highly reflective mirror, but a mirror all the same. And it turns out that the shape of this mirror, the cornea, is pretty well known. It's studied in physiology. It's ellipsoidal in shape with pretty strict parameters for a normal adult cornea. So we know the shape of this mirror. So what you can do is find this border right here. It's called the limbus, between the cornea and the white part, which is called the sclera. You find the limbus. Once you've found this limbus, in any photograph, if you're able to do this, it's a high enough resolution, high quality photograph. If you're able to find the limbus of any eye in there, a normal adult cornea, then you have found the location, the position and orientation of this ellipsoidal mirror with respect to the camera that was used to capture the image. And now you can go in and take the information inside the cornea and map it into a wide-angle image of the world around the person. So here are eyes looking off in different directions. And in each case, we find the limbus. Now, of course, the parameters of this limbus, which is an ellipse, would depend on which direction the person is looking in with respect to the camera. So we can take the information inside the cornea and map it into a wide-angle image or an environment image, and those are the images that you see here. You can see here that these images have different shapes. In other words, they have different fields of view. And the reason is the field of view of this system, which we will call the corneal imaging system, depends on the direction that the person is looking in with respect to the camera. That is, it depends on the orientation of your ellipsoidal mirror with respect to the camera. That's why they have different shapes. But interestingly, the shape, the field of view itself of each one of these images is actually quite a bit larger than the field of view of your eye itself, the light that enters the eye and the field of view of the eye itself. But anyway, let's come back to the limbus here. As we said, the parameters of the limbus tell us which direction the person is looking in with respect to the camera. That information can be used in conjunction with this very large field of view environment image to get an estimate of the image that is falling on the fovea of the person's eye. In other words, without implanting a chip inside this person's eye, you're able to just from a photograph of them figure out what they are looking at. And these are called retinal images right here. This person's looking at the CNN logo. We know this because we asked this person to look at the CNN logo. This person is looking at the man on the right, and this player is going for the yellow ball right here. Okay, so I want to share with you an example of this technique, which is interesting. There is a society called the Daguerrean Society, and this society has some of the largest collection of some of the earliest photographs, daguerreotype photographs that have been captured. So this one is from 1845, almost immediately after the daguerreotype camera, the film camera was first invented. So what the society has done is used this technique that I just mentioned, which is estimating the world around the person, to go into the photographs which have reasonably good eyes in them and try and figure out what may have been around the person back at that time. In this case, use one of the eyes of this grumpy old man to figure out what may have been around him back in 1845. So here is the mapping from one of his eyes, this man's eyes. You get this environment image. And here is an artist's sketch or rendering of what he or she believes may have been in the scene back in 1845. There's no way to say for sure, but the interesting thing is that if you stare at this long enough, you will tend to be convinced that indeed this is a reasonable explanation of what was going on back in 1845.